So in this video, we're going to take all of the individual transformations that we talked about in the first 5 videos, and we're going to apply them at the same time to graph transformations of toolbox functions. And we need to do this, we need to apply the transformations in a particular order. So we're going to look for horizontal shifts first. We're going to look for X and Y axis reflections second. We're going to identify stretches and compressions in step 3. And then we're going to look for vertical shifts in step 4. So here's an example. I have a function g of x that is a transformation of the toolbox function f of x equals the absolute value of x. So I see the absolute value functions being used, and this means that the function g of x can be built from the toolbox function, the absolute value of x. So I want to look at g of x and identify first, have any horizontal shifts been done? And that was done by looking at the input variable x and identifying is anything being added or subtracted to the input variable. So in this case, we're adding 3 to the input variable x, which indicates that we have a horizontal shift 3 units to the left. 3 units left. Now look for reflections. And in this case, I can see that there's a negation happening to the outside of the function, to the absolute value function itself. And that indicates an x-axis or vertical reflection. So those are all the reflections that we see. Now look for stretches or compressions. So I need to, for stretches or compressions, I'm looking to see, is there a number outside of the absolute value symbol being multiplied to it that has an absolute value greater than 1. In this case, there isn't. So there's no stretch or compression. And then I want to look and see, once I've identified there's no stretches, I would look and see if there's any vertical shifts. And so I have a 2 being subtracted from the absolute value function, which indicates a vertical shift of down 2 units. So once you've gone through and identified the transformations that have been applied to your toolbox function, f of x in this case, we want to draw the toolbox function, the absolute value function, into the grid. Like we did in the other videos, we want to identify some key lattice points on that function. So we'll take the point 1, 1, we'll take the point 0, 0, and we'll take the point negative 1, 1. And we're going to apply the sequence of transformations to it. So the first transformation was move the graph 3 units left. So take each point and move it over 3. We'll take this point now, move it over 1, 2, 3. We'll take the origin and move it over 1, 2, 3. So that takes care of the horizontal translation. Now we need to do an x-axis reflection. So reflect this point in the x-axis, reflect this point in the x-axis. This point will be stuck on the x-axis. There's no stretches or compressions. And now move those 3 points down 3. So we'll grab him and go down 1, 2, 3. Take this point, move him down 1, 2, 3. Take this point, move him down 1, 2, 3. And we've taken care of all of the transformations, so we draw in the final graph as nicely as we can, preferably with a ruler. That's good enough for government work this early in the morning, and this is the function g of x, which is a transformation of the toolbox function f of x equals the absolute value of x. So the next example, I'll look here and I see that I have a square root function. So my toolbox function is f of x equals the square root of x. And this function's been transformed to make a new function g of x. Again, we go through and identify the sequence of transformations, look for horizontal shifts. So right here I am subtracting a 1 from the input variable, which will be a shift of 1 to the right. Now look for reflections, and in this case I have a negation on the input variable, which is a y-axis reflection. And I have a negation on the outside of the function, on the square root function itself, and that causes an x-axis reflection. So we've identified the x and the y-axis reflections. Now look and see, are there any stretches or compressions? And in this case there's a stretch by a factor of 2. So everything is doubled in sides. So we stretch by a factor of 2. And 4, we look to see, are there any vertical shifts? And there is a vertical shift. I have 3 being added to the square root function, which is going to shift everything up 3 units. And now that I've identified the transformations, I go to my toolbox function. Here's the square root function, the basic standard square root function. We draw in the lattice points. And then we apply the sequence of transformations in the correct order to those lattice points. So first transformation, move everything 1 to the right. So we'll take this point, move him 1 to the right. Take this point and move him 1 to the right. Take this point, move him 1 to the right. And then we need to do a y-axis reflection. So reflect this point in the y-axis, reflect this point in the y-axis, reflect this point in the y-axis. So there's the y-axis reflection. Now we need to do an x-axis reflection. This point stays put. This point will move to an output of -1. This output of 2 moves to an output of -2. So there's the x-axis reflection. Now we need to stretch by a factor of 2. So 2 times the outputs, 2 times 0, 0, 2 times -1 is -2. 2 times -2 is -4. Everything doubles in size. And then move everything up 3 units. So this point here will move up 1, 2, 3 units. And this will be the final point. So we get -1, 3. This point will move up 1, 2, 3 units to here. This is the point -2, 1, and this one will move up 3 units, 1, 2, 3, and land right here. And that is the point -5, -1. And then you draw in the transformed square root function, which is going to come pick this point up, swing down, pick that point up, and go off to -infinity. So same game. We have a piecewise defined function, which we haven't talked about yet this term, but we can still apply transformations. If this function is the function f of x, we've made a new function g of x by transforming f of x. So again, you just go through and look for the transformations. So horizontal shifts. So the only way to get a horizontal shift is if we add or subtract something to the input variable. Nothing is being added or subtracted to the input variable, so there's no horizontal shift. Now look for reflections. So to get a y-axis reflection, we would need a negative sign on the input variable. There isn't one. To get an x-axis or vertical reflection, we need to see that there's a negation on the function. There is. So this represents an x-axis reflection or vertical reflection. 3, do we have any stretches or compressions? We don't. There's no scalar other than a 1 or -1 in front of the function, so there's no stretch or compression. 4, do we have a vertical shift? Yes, we're subtracting 1 from the function, so this is going to move everything down 1. And so now you just walk through and apply those transformations to the points on the function f of x. No horizontal shift. X-axis reflection, we'll take this point and reflect it down. We'll take this point and reflect it down. And we'll take this point and reflect it down. So instead of 4, we'll be at -4. We'll reflect this point down. And then what else do we have? We had no horizontal shift, x-axis reflection, no stretch or compression, and now move everything down 1. So move it down 1 into the final position. This will be 3, -3. Move this down 1 into its final position at -1, -3. He moves down into the final position at -2, -5. This one moves down into his final position at -4, -5, and then draw in your function. So we'll draw the straight lines connecting the points. And this is the final function, that is the transformation of the original. I called him g of x. This was the original function f of x. And last example, we'll take the same function that we just looked at, and we'll create a new function g of x by transforming it by multiplying a half of the function, evaluated at x minus 1. It's not even Monday. Oh, x plus 1. So again, walk through, look for horizontal shifts. We're adding 1 to the input variable. That moves the graph 1 to the left because we're adding 1. 2, any reflections? So we're looking for a negation on the input variable or a negation in front of the function. We don't see a negation in either of those places, so there's no reflection. 3, do we have any stretches or compressions? Yes, we have a compression. We're multiplying all of the outputs by half. We're making everything half as big as it was. So compressed by 1/2. Any vertical shifts? So vertical shifts, we're looking for, are we adding or subtracting anything to the function? And we're not. So there's no vertical shift. And now go through and just apply the transformations. Move everything 1 to the left. So this point will move to here. This point moves, to the left, and I just moved it to the right. Move him 1 to the left. Move this one 1 to the left. This one moves 1 to the left. This point moves 1 to the left. No reflections. Compressed by 1/2. So he's at 4. So half of 4 is an output of 2. Half of 2 is 1. Half of 4 is 2. And half of 2 is 1. And now we can go and draw the final function, and let's label those ordered pairs actually first. This is -5 and 2. This is -3 and 2. It's good to label them as you go so you connect the right dots. And this is -2 and 1, and this is 2 and 1. And so we'll draw the straight line connecting those, the line connecting those, and the line connecting those. And there's the final transform function g of x.